Okay, we will now look at the asymmetrical machine and the use of generalized rotating field theory, and see how this theory can be applied for some practical situations in case there is a symmetry in one or two of the members. Okay. What we identified in the earlier lectures is that if both stator and rotor are asymmetrical with m stator winding and n rotor windings, short circuited rotor, then the stator currents will give rise to fundamental frequency gives rise to forward and backward fields, and they will interact with the rotor windings, and that will give rise to forward field will give rise to F minus Fr, backward field will give rise to F plus Fr. Okay. And this F minus Fr, the frequency current will again give rise to two fields, one forward with reference to rotor. So, forward will be in synchronism with the inducing field. So, it will induce a frequency f with the stator, and the backward field will again induce another frequency f minus 2 Fr in the stator. Okay. So, each field will give rise to two frequencies in the other member, right. So, we have f minus Fr, f minus 2 Fr, f minus 3 Fr, that chain continues, and on the side f plus Fr, f plus 2 Fr, etcetera continues, right. Then we can argue the following cases. Okay. Now, if the what we recapped the last lecture was that if we have, let us say, a rotor symmetrical, of course stator asymmetrical, right, then what will happen? Now, it will give rise to stator asymmetrical, means it will give rise to forward backward field, of stator, and which give rise to what? This will give rise to f minus Fr, f plus Fr in rotor, right. This f in stator will give rise to this, right, and rotor is symmetrical. Rotor symmetrical means this field, there is a rotor forward field will be at, due to f minus Fr, right, because rotor is symmetrical, therefore, it will give rise to only a positive sequence currents of frequency f minus Fr, is not it, only positive. So, that will only give rise to f only in stator, right. That it cannot induce any backward field with reference to rotor, because there is already a positive sequence current in the rotor. Is it clear? Then you look at the rotor backward field. That means that is due to f plus Fr frequency, but that will be at a negative sequence, because that will be due to the backward field, and that those currents will be a negative sequence, means it will rotating backward, and that will be in synchronous with the inducing field, which will only result again in f in stator, is not it? Okay. So, if you want to show, say, symbolically, the fields omega minus omega due to stator, is not it, and which will result in omega minus omega r, okay, and omega plus omega r, two fields. Okay. Now, this rotor frequency of omega minus omega f r f minus f r will give rise to another field which will be at omega with reference in the air gap, because it is positive sequence, and another will be only at minus omega, right, because this is due to the negative sequence in the rotor bars, this is due to positive sequence in rotor bars, and that will give rise to one field which is forward rotating, another will forward. So, these two will be at synchronism and these two will be at synchronism, and which will produce a torque, and this we call it as the forward torque T1, this will be the backward torque T2, is not it, due to the interaction of the stator forward field and rotor forward field in the one side and rotor backward field and stator backward field. Okay. Now, there is no way, so the frequency induced in the stator will only be f due to these fields, because these fields are at a speed of plus or minus omega with reference to stator windings, right. Is it clear? Therefore, there is no further induction takes place in view of this, because rotor is symmetrical. Rotor is symmetrical, therefore, there is no way a further backward field can be created out of the induced currents, right. So, there is no further induction into the stator. So, the only frequency you will have is f plus or minus f r, that is all it will terminate at that point. Okay. Now, next you can also extend the logic, you say stator symmetrical and rotor asymmetrical. Stator symmetrical, rotor asymmetrical, right. Then what do you expect? Rotor is asymmetrical. Okay. So, I draw the rotor asymmetrical. Okay. Is this the air gap? Now, stator is symmetrical, right. So, it will only produce, let us say, a forward field, it does not produce a backward field, symmetrical and assuming a balanced supply, right, assuming a balanced supply, forward field is produced, and that will give rise to omega minus omega r or f minus f r in the, so it will only be positive sequence, because bars this is only due to forward field, okay, and this positive omega minus omega r will give rise to two fields, okay, this f minus f r will give rise to omega minus omega r and minus omega r. This rotor current of frequency f minus f r flowing in a asymmetrical rotor will again give rise to two fields at a due to the frequency f minus f r, which will be at plus omega minus omega r and minus omega minus omega r with reference to rotor, because the rotor is at omega r. Rotor is rotating omega r. So, there is a field which is at a speed of omega minus omega r with reference to rotor, which would mean it is omega with reference to stator. Rotor field will be one side will be omega with reference to stator, and the other side will be, because it is minus omega minus omega r, which will say it is equal to omega minus 2 omega r. Because it is at minus omega r, rotor is rotating at this side, so it is a difference in this, okay. That will give rise to a frequency f minus 2 f r in the stator, because stator will now see another additional field rotating in the opposite direction, okay, and which will be at omega minus 2 f r, omega 2 omega r, which will give us f minus 2 f r backward. Now, this field will induce again balanced currents in the stator, because stator is balanced, right. This field will give rise to balanced currents in the stator, and that means it will again give rise to another field in the stator, which is synchronous with the inducing field, isn't it? But it will not create any more negative field, because stator is symmetrical. It will only give rise to one field only, because the stator is symmetrical, okay. So, that is what it will happen, right. So, we find here in this model, stator will have frequency f minus 2 f r, and rotor will have frequency what? What rotor frequency will be? F minus f r only. Now, supposing there is stator has unbalanced supply, what will happen? Somehow your stator winding is symmetrical, supply is unbalanced, then what will happen? What will it happen? What type of fields it will create now? Stator currents of frequency f unbalanced will give rise to what fields? So, if stator will produce forward field at plus omega and backward field at minus omega, the stator fields, right. Okay. And whatever plus omega, whatever happened was here, but then you have additional fields due to minus omega, right. So, you will have in this case, if you same logic if you extend, stator will have f plus or minus 2 f r, and rotor of course will be f plus or minus f r, because the both forward and backward field will give rise to, there are two additional fields. The frequencies will be added, one extra in stator and one extra in rotor, because rotor currents asymmetrical, because forward field will also induce a current, backward field will also induce a current. Okay. So, this is the sequence of arguments and logic you need to understand, how the air gap fields will induce currents in stator and rotor appropriately. And then last case is stator and rotor symmetrical, okay, and balance supply. Okay. Then you know it is a very typical case, right. You have plus omega here and omega minus omega are here, okay, and this will give rise to one field symmetrical. That means stator is f and rotor f minus f r. This is the frequency. Okay. Now, you have the another case of the same stator and rotor symmetrical, but supply unbalanced. This is also a case, no? Then what will be additional thing? Both are symmetrical, huh? So, there will be both forward and backward field in the air gap because of unbalanced supply, which causes what? F minus f r and? So, there will be stator is f only, rotor is f plus or minus f r. agreed. So, additional currents are there, right. So, there will be fields, there will be omega here and there will be another minus omega here, 2 stator fields and 2 rotor fields, and that will produce positive and negative torque. Otherwise, if it is balance supply, this whole thing would be absent. Is it okay? I am trying to just give you a physical explanation, okay, more a qualitative explanation. Okay. I think this is a very fundamental and basics you should try to understand. Any doubt at this point of the nature of fields in both asymmetrical symmetrical machines with both symmetrical and unbalanced or unbalanced supplies. Okay. So, we have already, I am just recapping, we already know that the equation for the voltage equation will be, we have voltage matrix will be RS, leakage reactance, they are all referred to the corresponding frequency F1. Then we defined a coefficient matrix, forward self coefficient matrix, backward self coefficient matrix. So, which will be MS and MS star, then this is MSR and MSR star, okay, for the frequency, right. Is it okay? This we wrote last lecture. Then we wrote this will be when it is referred to the fundamental frequency f by f1. So, this will be RR or f by f1, they will all be, this will all be corresponding to the base frequency. Okay. Vs f by f1, MS, MS star and MSR star, okay, fine. Then we said that, so MS into XF and MS star into XB are the mutual reactance matrix due to forward and backward fields. Okay. And MSR XF and MSR conjugate XB are the mutual reactance between the stator and rotor due to forward and backward. That means between stator and rotor, mutual reactance between the stator and rotor. Okay. Now, we wrote what is this MS, we have explained last time. MS is the self reactance which will be between all the windings S1 to SM. I hope you have understood this. How do you get due to forward and backward fields? If it is forward field, this is MS and its conjugate to the backward field. MSR will be a product of these two, that means it will be the turns and the displacements, and we have the rotor terminals here. Okay. Then similarly for rotor voltages, of course, this should be 0 normally. You can rotor voltage equation we also write resistance, mutual leakage reactance, then its own self reactance MR and MR star XB into IR of that frequency F2. Then it will be the induced voltages due to MSR transpose conjugate XF, MSR transpose XB into. So, a frequency F2 in the rotor is due to its own frequency F2 in the rotor, plus there is a stator frequency F2 plus Fr and other stator frequency F2 minus Fr. Both of them will induce this. Okay. Then we defined MRXF and MR star conjugate XB are the self reactance matrix due to the forward and backward fields of the rotor. Okay. And MSR transpose XF and MSR transpose conjugate XB are the mutual between the rotor and stator due to forward and backward fields. Okay. So, these are the terms you have used because we have large number of equations to handle. And of course, we have the rotor coefficient matrix MR, which is already explained in the last lecture, and then you have the I mean, of course, we know these are the statements that normal induction machine stator is equal to the applied voltage, and for all frequencies the voltage is 0. Now, the asymmetry in stator and rotor results in large number of frequencies. Now, if only one member is symmetrical, then number of frequencies gets reduced. This is what we have now thought of. If any one becomes symmetrical, it truncate at that point. Okay. If you have said if the rotor is symmetrical, then stator field induced will be balanced polyphase currents in the rotor. The forward field produces positive phase sequence and backward produce negative phase sequence. Okay. Then balanced currents in the rotor will produce no backward field. So, there will no further reduction in the frequency, that is what we have done. Okay. Now, similarly, if the stator is symmetry and if polyphase currents are impressed on the stator winding, there will be no backward field due to stator currents. This is what we have done, no backward field due to stator currents. Then due to asymmetry in the rotor, stator field produces unbalanced currents of F minus Fr in the rotor, which produce both forward and backward fields, and forward field is synchronous with the inducing field, and the backward field, and if the stator is fed from unbalanced supply, then we say the additional frequencies are there. So, it will have F plus 2 Fr induced, again this we have already discussed this. Okay. The induced frequency currents of F plus 2 Fr in the stator will be balanced by the symmetry of stator and no further induction will take place. Okay. Now, for symmetrical rotor machine, fields producing in the direction of rotor will induce balanced N phase currents, positive sequence currents in the rotor windings. So, if it is rotated in opposite direction, it will have N phase negative sequence currents. It depends on which direction you rotate the rotor. Okay. If you rotate the opposite way, then it will be negative sequence. Okay. Now, if the symmetrical rotor machine, supposing we have a symmetrical rotor machine, what is a symmetrical rotor machine? All the resistance are same. What is symmetrical rotor? You have N windings, all resistances are same, all leakage reactances are same, say XR, and the turns are same, KR1, KR2, KRN equal to let us say KR, rotor turns are same, right, and the phase displacement will be equal, right. So, what will be alpha r will be e to the power 2 pi by n, is not it. If it is symmetrical n phase machine, the theta will be 2 pi by n and alpha will be e to the power of j 2 pi by n. That will be the angle of the different windings, and your MR will become much more simple. You have 1 alpha r to the n minus 1, alpha r minus 1, 1. So, all your diagonal matrix will be unity, all others will be reflecting the phase disposition of the respective windings with reference to the reference winding R1. Okay. So, this is your self reactance coefficient matrix, okay, that is Kr square into this. Okay. Now, MSR is just a substitution. MSR will be first one will be 1 into alpha r to n minus 1, then there will be Ks2 alpha S2, Ks2 alpha S2 alpha r, etc. So, you have Ksm alpha S. If you see Ks1, Ks2 are the Ks2, Ksm are the turns of the stator windings with reference to S1 winding, stator winding. Okay. Then Ksm alpha Sm alpha r and so on. Agreed? So, we have got this MSR matrix. Now, there will be stator voltage for frequency f minus 2 fr in the stator will be this will be the voltage equation, which is for the stator frequency. Okay. Now, if symmetry in the rotor alone, this term MSR conjugate XP IR F minus FR is the forcing voltage which that causes the stator currents of frequency f minus 2 FR, because there is one forcing voltage. Rotor current will in turn give rise to f minus 2 FR in the stator, but if the field itself is not there, nothing will be produced. Now, what is that field? You can prove that MSR conjugate XP IR will be just as supplying F in the stator causes currents F plus or minus FR. So, we have to see what will be this value after substitution. Okay. Therefore, you will notice, for example, that symmetry in the rotor alone, this term MSR conjugate XP IR F minus FR, this will become 0. I want you to verify this, because IR itself is of IR of F minus FR, because rotor is symmetrical, is itself a balanced current. Now, you just find out this. Okay. Anyway, this we assert frequency F minus FR, positive sequence, F plus FR, negative sequence. Then the IR of F minus FR, rotor current of frequency F minus FR will be its magnitude into this 1 alpha to minus 1 alpha minus n minus 1 etcetera, which would mean it is balanced currents of n phase balanced currents. Okay, because it is due to positive sequence, right. So, if they will all be in this phase, say let us say R1, R2 etcetera, it will come balanced currents. Okay. And other one, negative sequence, if there is a backward field, they will also balance current, that will be negative sequence. Negative sequence means if you have R1 here, so the IR1, IR2, then go to IRN, is not it, and this angle is 2 pi by n. Okay. The balanced negative sequence currents. So, that will again further will not induce any more currents. Okay. Now, so MSR conjugate XB IR F minus FR is 0. So, there will be no further induction, F minus 2 FR will not be there, F minus 3 FR will not be there, F minus 4 FR will not be there, right, because this itself becomes 0. Okay. Now, similarly for stator currents of F plus 2 FR, this term itself is 0. A frequency F plus FR, the negative sequence, this term MSR XF into IR F minus FR is 0. So, it will not induce F plus 2 FR or F plus 3 FR or F plus 4 FR. So, it will not induce further. Therefore, there will only frequency F plus or minus FR in the rotor. Okay. Therefore, performance equation gets simplified. Okay. So, what are the performance equations? You have to write 3 equations only. one for stator frequency f, okay, which is given by this Rs, Jxs, Msxf, Ms star xb, and rotor frequency one is due to f minus fr, another is due to I think it should be f plus fr. Okay. This will be the stator frequency, this will be the voltage equation. Okay. Similarly, you can write the rotor voltage equation for f minus fr, right. This will be Rr f minus fr due to the rotor current, its own currents are f minus fr, and plus the stator current f and stator current f minus 2 fr. And we have discovered that the other current is not there. Okay. Rotor voltage f plus fr is this, this will be okay, this is equal to f plus f, I think this is a wrong equation actually, Vr over f plus fr I think we have to rewrite, sorry, I am sorry, we have to rewrite this equation. So, basically you have to write 0 equal to Vr f over f plus fr equal to Rr f over f plus fr plus jxr plus j times mr star xb into IR f plus fr minus j times MSR transpose xb is into f. Okay. So, we have three equations, stator one equation, rotor two equations. Okay. Okay. Now, symmetry in stator alone we have already discussed. How many equations will be there if symmetry in stator alone? How many equations? Rotor is asymmetrical. How many frequencies are there? Stator has two frequencies, f and f minus 2 fr. Rotor has one frequency, f minus fr. So long as their supply is balanced. Okay. And stator symmetry would mean stator resistances are same, stator leakage reactance are same, number of turns is same. Stator symmetrical means, right? Stator symmetrical means they are all same, isn't it? Okay. And the phase displacement is same, e to the power g j 2 pi by sorry, it is m alpha s. Okay. Right. And then you can write down, substitute ms, right, you can get this. Then you have MSR, again it is a simplified equation, it is a substitution of the earlier terms basically. And then you write, you have the rotor equation for frequency f plus fr, okay. And you can show that this term is a forcing stator voltage which induces f plus fr. We want to know whether there is f plus fr or not, okay. And I think you will discover that the rotor current of frequency f plus fr is 0, because stator is symmetrical, right. And the currents are balanced of frequency because stator is symmetrical, stator currents are balanced currents of M phase. Now, the forcing voltage becomes a null matrix. So, there is no current of frequency F plus Fr, right. In fact, if you look at the equation, you will see that current becomes 0, right. Therefore, all induced currents when F plus Fr of rotor is 0, its subsequent currents will be 0, F plus 2 Fr is 0, 3 Fr is 0, 4 Fr is 0, they will all be absent. Okay. All the other currents will not be there. Okay. Okay. Now, if you write an equation F minus 3 Fr, again you can know that the forcing voltage is 0, the currents of frequency F minus 3 Fr in the stator will be absent. There will be no, while you have F minus 2 Fr in the stator, it will not induce F minus 3 Fr in the rotor. Therefore, for balanced supply, there will be F in the stator, F minus 2 Fr in the stator, and there will be only F minus Fr in the rotor, no other frequency currents. So, you have to write only 3 equations, okay, right. What are 3 equations? You have VSF, okay, RS plus JXS plus MSXF ISF, then there is only other frequency is F minus Fr, right, there is no F plus Fr, okay. So, MSR XF into IR into F minus Fr, that is what you have, okay. Then rotor will have 2 frequencies F minus Fr, again you write F minus Fr, the current F minus Fr, and it will be due to 2 stator currents. One is the stator current of F, another stator current of F minus 2 Fr, right. There are 2 stator currents now, that will induce a frequency F minus Fr in the rotor, and rotor is asymmetrical. There is another stator current F minus 2 Fr, for that you must write a voltage equation, but that is voltage induced is 0 because for other frequencies the supply is short circuited, okay. Then this is RS over F over F minus 2 Fr plus JXS, then this is due to its own current F minus 2 Fr, but also due to the rotor current F minus Fr, okay. So, you have 3 equations for the stator, for the machine, 2 for stator, 1 for rotor, okay. Then if the stator, if the supply becomes unbalanced, as we said, there will be additional frequency F plus 2 Fr, F plus Fr, F plus 2 Fr, but there will be no F plus 3 Fr, it will terminate at F plus 2 Fr if the supply is unbalanced, okay. So, there will be no F plus 3 Fr, F plus 4 Fr, F plus 5 Fr. So, additional frequencies F plus Fr in the rotor and F plus 2 Fr in the stator, that we have already discussed. If the supply is unbalanced, what are the new frequencies, okay. Now, if they have symmetry in stator and rotor, then you are much simpler, your MSR becomes a simple matrix, okay, MSR, then there will be no F minus 2 Fr, F minus 3 Fr or F plus 2 Fr, F plus 3 Fr, they are all not there. So, only F in stator and F minus Fr in rotor, if both are symmetrical, right. Then you have to write only 2 equations for frequency F and frequency F minus Fr, okay. It is just a substitution of the general equations. That means, if you write a general equation, you make a particular case of symmetry and add on to this, okay. Now, okay, if the supply is not balanced, then this term will not be 0 and rotor current of F plus Fr will be present. If supply is not balanced, there will be a negative field because this will not be there, okay, will not be 0, therefore, F plus Fr will be present, okay, right. Now, we will try to see whether can dovetail also symmetrical components into this. Okay. And we have, you are already aware of symmetrical components. What are symmetrical components? You have a symmetrical components y of a x by multiplying by a matrix x, which is a complex matrix, is not it. So, symmetrical component is a method where you make even real terms complex. So, y are the symmetrical components of x, okay. And if these are the m phase quantities, m phase symmetrical components, then it will be, what are the quantities? 0 sequence, first sequence and m minus 1 sequence. Okay. These are the 0 positive and negative sequence you see m minus first is the negative sequence actually, right, m minus 1 is the negative sequence, y 2 is not negative sequence, it was some other sequence. Okay. So, this is a m phase symmetrical components, and the matrix for m phase symmetrical components will be 1 over m 1 alpha is to m minus 1, 1 alpha is m minus 1, alpha is m minus 1, m minus 1. Put m equal 3, you get the 3 phase symmetrical components, and m equal to 2, what do you get? Put m equal to 3, you get 3 phase symmetrical components here. It is m phase symmetrical components. M equal to what do you get? M equal to 2, 4 phase. So, if you want 2 phase, you have to put m equal to 4, right, semi 4 phase. Okay. Okay, that right. So, you can try this, what is this thing. Okay. Now, if the symmetrical state, if the symmetry in stator, these are the quantities, okay, and for an M1 winding machine, stator you can transform by Sm, rotor by. So, what you do is, if there are symmetrical, you put symmetrical component transformation to stator for M phase, rotor to N phase, okay, and Sn is a n by n matrix, that is n phase symmetrical component similar to Sm. Okay. So, pre multiply this by this one Sm Vsf, okay, and Sn Vr, because they are all balanced currents and balanced voltages. If you do this, okay, multiply by this Sm and Sr, you will have this equation. What we are trying to say is stator symmetrical, rotor symmetrical, stator has balanced currents, rotor has balanced currents. All I do is from the original equations of Vs and Vr, Vs for F and Vr for F minus Fr, I apply symmetrical component, multiply by this, and I have Vs plus, that is the positive sequence voltage for stator will be Rs plus Jxs Is plus Jmxf Is plus minus Jnxf Kr Ir plus, okay, and 0 is equal to Vr plus by S, Rr by S and Ir plus, then there is Ir plus, and this is due to the mutual currents in the stator. Okay. So, you will have a simple, okay, Vs plus Vr plus is positive sequence, Is plus Ir plus is the currents, stator rotor currents. I think you are, I am do not want to waste much time because you are aware of this. We have done it for 3 phase, it is just for M phase. Okay. Now, you can refer the rotor current to stator, that you are also aware. How do you refer? Now, you have to refer first the phases also. Rotor has N phase and stator has M phase. So, you have to multiply by N by M. So, it is equivalent to saying I want to have the same number of phases as the stator, okay, into this, and we have Vr dash and XR dash and RR dash XR dash. How do you transform the voltages, currents and impedances? Now, you have to be careful, you have to multiply by the phase transformation also, phase numbers n by m. Okay. If you do all the jugglery, you get very nice equations. Vs plus is equal to Rs plus Jxs Is plus Jmxf Is plus minus Ir plus dash. Okay. Then you have Vr plus dash by S is Rr dash by S, Jxr dash Ir dash plus Jxm into Ir plus dash Is dash. So, what does it give you? What is that? It is a symmetrical machine. What will it give you? Huh? What will this equation? Okay. So, you have the this is Vs plus or positive sequence voltage and Is plus Ir plus Rr dash by S, Rs maybe Jx1 or whatever, what did we call Jxs, sorry, Rs Jxs, Jxr, and what is this? J times Mxf. I think this is important. See, our Xf was defined for one phase. So, it is very important for you to know what we have got here. Okay. So, J mutual reactance will be Mxf because M phase machine. Okay. Right. The Mxf is the reactance of stator winding due to mutual flux between stator and rotor. Okay. This is Mxf. Now, we have already done analysis of two phase machine with asymmetrical stator winding in quadrature, is not it? You can do the two phase, you can do the similar thing. So, you have Vs plus Vs minus in terms of Vs1 Vs2. I have two phases S1 S2 and again you do the same jugglery Is plus Is minus. This is due to the two phase symmetrical component transformation. If you do this, you have this Vs plus is equal to Rs1 plus Jx1 Is plus Rs2 dash Jx2 plus Zd dash Rs from Jxs1 Is plus Is minus 2jxf into Is plus and Ir plus. Okay. So, then you have Vr dash by 2 minus S, Rr dash by 2 minus S, Ir dash, then Ir minus dash, this Ir minus dash, Is minus dash, then rotor values are referred to stator. Okay. So, I have written expression for the stator and rotor. Okay. So, what will it give you? See this equation we have written how many? 2 minus S we have written for x and this, okay, and we are expected to, so we have Vs plus, okay, so two phase we have done it. So, you are also able to get it in the same manner. So, Vr dash 2 minus S, this is Rr dash by 2 minus S. So, you have Rr dash by 2 minus S, maybe Xr dash, this is twice Xf, Rr dash by S, this will be twice Xf, okay, and this one we call it as Is plus IS minus, I mean some earlier we call ISF, ISB, etc. So, it is the same, you are fairly familiar with this equation, and that has been obtained by the same, and you have a, these are the rotor equations, and this is the stator equation, you have this Vs plus Vs minus, is not it. We got Vs plus, which will have a linkages, you know, between stator and rotor, and also positive and negative, you have a impedances, etc. Okay. So, we got some linkages between the stator and rotor, positive and negative sequence will have the linkages. Okay. Now, if we do the same exercise for asymmetrical rotor with symmetrical stator, what we are trying to do is, this is actually practical case for most of the crane drives. To start with, what they do is they do an external resistor, but they are not equal resistors. See, what they do is, you have the crane drive, you have this, they are all mostly slip ring machines. So, you connect some resistances, but these are not same. So, external resistance RE1, RE2, RE3. Okay. So, RE1 is not equal to RE2, not equal to RE3. So, this way it becomes asymmetrical, is not it. So, you can add this to the resistance, internal resistance of the windings, and it becomes asymmetrical machine. Okay. Yeah. It is supposed to give a better torque profile for at starting and controlling the currents, you know how you do it, etc. You know, in fact, this was the suggestion made by Russians to some of the Indian companies who supplied the mining equipment, and also for crane drives. Okay. And it in fact, it is a quite an involved theory, in the sense the reason for this, basically you want to have a good starting torque and also limited starting current. Yeah, that is what what is being proven. Okay. Maybe you have to work it out, you might have to develop a program perhaps, okay, to do this. Therefore, if you want to analyze with asymmetrical rotor, so you can do the same thing, you have Vs plus, you can write the expression, and you have Vs minus, that is because of 2s minus 1, there is another frequency in the stator, one will give rise to positive sequence current, another gives rise to negative sequence currents, right, and you write this equation, right. You have two equations in stator, and you also have two equations in rotor, both are a slip frequency, rotor frequency is only one. Okay. But there will be, rotor will have both positive and negative sequence currents, because rotor is asymmetric. Rotor will have both positive and negative sequence currents, and its voltage equations are written like this. Okay. What do you observe by this equation? This is the equation we get by applying symmetrical components. So, what do you observe here is, the rotor positive sequence will have its own positive sequence current plus a coupling between IR plus and IS plus, coupling between IR plus and IS plus, then also IR minus and IS minus. So, this is the coupling impedance, right. Similarly, there is a VR minus dash, that will be between IR minus and IS minus, and then there will be another between IR minus and IS minus, like that. So, there is a coupling impedance here. Okay. So, from this what you can get is, this is about the frequency f, is not it, right. Then you have maybe it will be something of a T network here, this will be stator frequency f minus 2 fr. This will be Is plus IR plus IR minus Is minus. Okay. So, you will have this equation and you can find out, you have the 4 equations with you, you can write an equivalent circuit of the 4 equations with 4 quantities Is plus Is minus IR plus Is minus. I have written to you all right. So, this will be f frequency f minus fr, f minus fr, this will be f minus 2 fr, all refer to stator frequency. Okay. So, you can, I suggest you derive this equivalent circuit. Okay. Anyway, this we have discussed in the paper in little more detail. So, I want you to read the paper, get this equivalent circuit, get these equations, derive these equations, okay. And I would now expect you to at least derive these last equations from the original equation, okay. That will be your assignment. Is it clear to you? You work out, it is basically a simplification, because in the paper many derivations are not given, it is only say from this you get this, but you should convince yourself that yes, it is correct. So, whatever is in section 4.1, 4.2, 4.3 equation, in these sections, have you understood? Section 4.1, 4.2, 4.3 derive the equations, right. That is important. Section, there are all only those equations given here, is it okay? Section 4 in the paper from the original matrix equation, right. Okay, we will stop it here now. Okay.